In last class, we completed 3 bits in first problem of exercise number 1.1 in relations and functions. In this class, I am going to do another 3 bits. Last 3 bits is something like not reflexive, not symmetric, that type of problems. In this class, whatever the problems I will do, they are reflexive, symmetric and transitive. As we discussed earlier, when it is not reflexive, it is very easy to write the answer. We will give a counter example why it is not reflexive. When it is not symmetric, then it is very easy to write the answer. We will give a counter example why it is not symmetric. But when the case comes when it is reflexive, when it is symmetric, when it is transitive, how to write the answer? We cannot, by giving a counter example, we cannot write the answer. So to understand these things, I am doing this as a part of 2 videos. Last 3 bits in 1 video. Last 3 bits I did last class. If you see the last class, the last 3 bits are like this. Counter example saying not reflexive, not symmetric. And these 3 bits, we are not giving counter example. We are generalizing. We are checking the complete property is valid or not. So you try to understand this 4th bit. See what they given. Relation R in set Z of all integers. That means they are saying that R is a relation on set of all integers, and the relation is defined as R equal to order pair x comma y such that x minus y is an integer. That is the information they given. So as we discussed in last class, 3 steps always common in every problem. First, this relation is on which set? Z. So I written Z. What is Z? Set of all integers. You know what are integers? 0, plus or minus 1, plus or minus 2, plus or minus. This is infinite set. Okay. Second point, this relation is from where to where? R is a relation in the set Z. That means R is a relation from Z to Z. Third point, how the relation is defined. All these 3 things we will get from the question only. The relation is given as order pair x comma y such that x minus y is an integer. Here you need to understand that x must be an integer, y is also must be an integer, that we discussed in last class also. Alright. So for any problem in this first question, these 3 steps are compulsory. We will write these 3 steps first, then only we will proceed further. Now, we need to check reflexive property. What is reflexive property? For any x belongs to A, the order pair x comma x belongs to the relation, then we say that relation is reflexive. Here, you take one element x in set A. What is set A here? Here it is not set A, it is set Z. You take an x in the given set. You check that order pair x comma x is there in the relation or not. See here, x comma x is there in this relation or not. Which order pairs will be there in this relation? See here, x is an integer, y is an integer, x minus y is an integer. You see, you take any 2 integers and subtract. Suppose 4, 3. Okay, 4 minus 3 is 1. Is an integer or not? What I am trying to say, when x is an integer, y is an integer, x minus y is integer or not, we are checking. You take x is 3, y is 4. 3 is integer, 4 is integer. 3 minus 4, minus 1. Minus 1 is integer or not? Yes, minus 1 is a integer. You can check that you take any 2 integers, subtract, again you will get a integer. No doubt in that. As we completed SSLC, we know this point. Subtraction of any 2 integers is always again a integer. Okay. So here I need to check reflexive property. How I will check reflexive property? X comma x is there in this relation or not? When x comma x belongs to R, when x minus x is an integer. X minus x. What is x? X is an integer. So here x minus x, integer minus integer, x minus x. Same integer minus same integer, x minus x. Try to understand here, x minus x. X minus x is what? It is 0. 0 is an integer or not? Yes, 0 is an integer. I hope you are understanding, right? So, what I'll say here, for any x belongs to z, if I take x is an integer, x minus x is what? X minus x is 0. 0 is an integer or not? It tells that x minus x is an integer. If x minus x is an integer, definitely order pair x comma x belongs to this relation. What you came to know that for any x belongs to z, the order pair x comma x belongs to the relation. Therefore, the relation R is reflexive. Now we will check symmetric property. What is symmetric property? You take an order pair x comma y in the relation. If y comma x also present in the relation, then we say that that relation is symmetric. You take an order pair x comma y in the relation. If the order pair y comma x also belongs to the relation, then we say that that relation is symmetric. Okay. You first consider one order pair in the relation. When order pair x comma y belongs to the relation, it means that x minus y is an integer. That is the set defined now. See here how the relation is defined. When an order pair x comma y belongs to R, it means that x minus y is an integer. You take an x comma y in the relation. Now you need to check y comma x is there in this relation or not. Okay, as x comma y belongs to the relation, x minus y is an integer. X minus y is an integer. We know that x minus y is an integer. See, what do you know about minus of x minus y? Suppose x minus y is 2. Suppose x minus y is 2. 2 is an integer. What about minus 2? Minus 2 is integer or not? Suppose x minus y is minus 2. Minus 2 is an integer. Correct? Yes. Minus of minus 2 is an integer or not? What I am trying to say, if x minus y is an integer, minus of x minus y is definitely an integer. Okay, multiply with minus, this will become y minus x. This expression you multiply with minus, this will become y minus x. Y minus x is an integer. Y minus x is an integer. So, you see here, if x minus y is an integer, then order pair x comma y belongs to R. Here what you got? Y minus x is an integer. If y minus x is an integer, what I can say? The order pair y comma x belongs to R or not? Yes, because y minus x is an integer. I hope you are understanding. What happened here? When x minus y is an integer, y minus x is also an integer. This means that if x comma y belongs to R, y comma x also belongs to that relation. See, what you got here, for any order pair x comma y belongs to R, we came to know that y comma x belongs to R. Therefore, you conclude, you write here, therefore, the relation R is symmetric. You try to understand, we are not giving counter example. This is generalized pattern. You see this also. I am not saying 2 is an integer, 2 minus 2 is 0, 0 is an integer, that's why it is reflexive. I am not writing answer like that. It is generalized way of writing. I am saying again and again, in this first problem, total 9 bits are there. If you understand all 9 bits, then you can do these problems very easily. Now, transitive property. What is transitive property? You take an order pair x comma y belongs to R and y comma z belongs to R. You take order pair x comma y and y comma z belongs to R. You need to check order pair x comma z is there in this relation or not. You need to check order pair x comma z present in this relation or not. Okay. X comma y belongs to R means x minus y is an integer. X minus y is an integer. From the definition of relation, see how the relation is defined. X comma y present in this relation means x minus y is an integer. Okay, here x comma y belongs to R means x minus y is an integer. Y comma z belongs to R means y minus z is an integer. Okay, what you know in this statement, x minus y is integer, y minus z is integer. Addition of two integers is again an integer. You check. You take any two integers, add them. Again it is integer or not? 100% it is an integer. Here this is an integer, this is an integer. You add both. What you will get? That is also an integer. So here minus y plus y will get cancelled. What you will get? X minus z. So x minus z is an integer. x minus z is an integer. Okay, so what you came to know, when you take x comma y belongs to r, y comma z belongs to r, you came to know that x comma z belongs to r. If x minus z is an integer, then order pair x comma z belongs to the relation as per the definition. I hope you are understanding. As x minus z is an integer, that means order pair x comma z belongs to this relation. X comma z belongs to this relation. So what you proved here, order pair x comma y belongs to r and order pair y comma z belongs to r, that implies order pair x comma z belongs to this relation. Therefore, this relation is transitive. What is transitive property? If x comma y, y comma z both are in the relation, then we will check x comma z is there in that relation or not. Here x comma z belongs to this relation. Therefore, this relation is transitive. I hope you are understanding. You can observe this problem. I didn't given a counter example. You see this last third bit. You see here, this is the counter example pattern. To prove symmetric property, 1, 2 is there in the given relation, but 2, 1 is not in this relation. So I am able to give a counter example so that saying it is not symmetric. When it is transitive, you see here, when it is transitive, I not given a counter example, right? Please go through that last video again, check those first 3 bits and check this 4th bit. In this 4th bit, we proved that this relation is reflexive, this relation is symmetric, this relation is transitive. Now we'll move to next bit. This is the 5th bit. Interesting bit. From now onwards, whatever the bits are there, they are somewhat interesting, easy to understand, right? If you can think intellectually, then it is easy to understand. Otherwise, these are difficult only. Relation R in set A. R is a relation on set A. What is set A? Set A of human beings in a town at a particular time. Given by the relation order pair x comma y such that x and y work at same place. Okay. First, as usual, 3 steps. What is set A? Set of all human beings in a town at a particular time. Okay. A is set of all human beings in a town. R is a relation from where to where? A to A. R is a relation from A to A. How the relation is defined? Order pair x comma y such that x and y work at same place. X and y work at same place. Now the question may arise. Here, order pair y comma z is there in this relation. Order pair y comma z is there in this relation. If you know y and z work at the same place, then order pair y comma z belongs to this relation. I hope you are understanding, right? X and y work at the same place, then the order pair x comma y will be in this relation. Okay. Now the point is, we need to check that this relation is reflexive or symmetric or transitive. Okay. First, symmetric property. What is symmetric property? You take an element in set A. You take x in set A. Now the point is, x and x works at same place. X and x works at same place. I am asking you, where you are working at that place only. It is a very silly question actually. Easily we can say, where x works there only. X and x works at same place means it is meaningful. Obviously, where is x is working, he is working there only. Yes, x and x works at same place. What it tells? X and x works at same place. That tells you that order pair x comma x belongs to this relation. Here what I came to know, if I take an element x in set A, I came to know that x comma x belongs to this relation, because where x works there only. Where you are studying that place only. You are not going some other place. Focus, right? This is easy, simple thing. Therefore, we can say that relation R is reflexive. Now, symmetric property. Is this relation is symmetric or not? First, I'll take an order pair x comma y in the relation. I'll take an order pair x comma y in the relation. Order pair x comma y belongs to this relation. What it mean? It means that x and y works at same place. X and y works at same place. Okay. x and y works at same place means y and x also works at same place. Think it is very simple to say. If x and y are working at the same place, obviously y and x also works at the same place. Clear it is. Where x and y are working, y and x also working at the same place. I hope you are understanding. If you know x and y works at the same place, we can easily say that y and x are working at the same place. If y and x are working at the same place, what I can say? I can say that the order pair y comma x belongs to this relation. The order pair y comma x belongs to this relation. So, for any x comma y belongs to R, y comma x also belongs to R. Therefore, we can say that this relation is symmetric. We can say that this relation is symmetric. Right? As you are able to say that order pair x comma y belongs to R implies the order pair y comma x belongs to R, then we can say that this relation is symmetric. Now we need to check transitive. Okay, transitive relation. Transitive relation, you take x comma y, y comma z in the relation. You take. Now you need to check x comma z belongs to this relation or not. If x comma y belongs to this relation, it means that x and y works at same place. X and y works at same place. Order pair x comma y belongs to R, it means that x and y works at same place. Order pair y comma z belongs to R means y and z works at same place. We know this statement now. You see, x and y works at the same place. Okay. Y and z works at the same place. That means where y is working, z is also working there. Here x and y works at the same place. Where y is working, z is also working over there. From this, after reading this statement, what you can say? Where x is working, y is working there. Where y is working, z is working there. That means x and z work at the same place. It's small logic, try to understand. X and z works at the same place, right? So x and z works at the same place means the order pair x comma z belongs to this relation. Therefore, this relation R is transitive. I hope you understand this. So this relation is reflexive, symmetric, transitive. You can observe here I didn't use any counter example. I generalized the things to explain these things, right? Now this bit I want you to try your own. What is this? R is a relation on set A of human beings in a town at a particular time. The relation is given like this. Order pair x comma y such that x and y live in same locality. It is similar to earlier bit. For example, first you write 3 points. What is set A? Set of all human beings in a particular town. What is second step? R is a relation from A to A. Third step, given relation. Is this relation is reflexive or not? X and x live in the same locality? X and x live in the same locality? Yes. So for any x belongs to A, order pair x comma x belongs to this relation. Therefore this relation is reflexive relation. Now to prove symmetric property, you take order pair x comma y belongs to R. If order pair x comma y belongs to R, it tells that x and y live in the same locality. If x and y live in the same locality, we can easily say that y and x also live in the same locality. No need of any bigger knowledge to say this. If x and y live in the same locality, y and x also live in the same locality. So this relation is symmetric. Next, a transitive relation. If x and y live in the same locality, y and z live in the same locality, obviously x and z live in the same locality. Therefore, order pair x comma z belongs to R. I want you to write the solution for this so that you will come to know how to write the solution for these problems. Another 3 bits are there. Those 3 bits I'll do in next class. I hope you understand this class. Thanks for watching this video. Have a great day. Bye-bye.